Hello students, in this lecture we will discuss the analysis of fuel air cycle.
See, if we talk about the design and study of IC engines, then I should say the analysis of engine cycle is an important tool. And as we all know, as we have read from thermodynamics, that thermodynamic cycle is basically defined a series of processes through which working fluid progresses and that eventually return the fluid to its original state. Also, we can say that thermodynamic cycle basically implies a closed system where there is no exchange of matter with the surroundings. But strictly speaking, the IC engine does not operate on thermodynamic cycle as it involves an open system with new substance or new fluid continuously brought in at one set of conditions, that is at the suction conditions, and released at another conditions, that is we are referring to the exhaust gases thrown outside. Okay, so the conditions are different for both the cases, suction and exhaust. However, the engine cycle have been analyzed as an open cycle, as though it were closed by imagining one or more processes that would bring the working substance at the exhaust condition back to the conditions of the starting point. Now one must be wondering why, after all, the accurate analysis of IC engine cycle is very difficult. And that is because of the complex chemical reactions that are taking place when the combustion is taking place, and moreover because of the friction and heat transfer present between the gases and the cylinder walls. So what is the way out? Therefore, the researchers or the analysts have made it a usual practice to analyze the cycle, making some simplifying assumptions. Simpler the assumptions, easier it would be to analyze the engine cycle. But even then, it would diverge from the reality. Now, the two usually employed approximation of actual engine are, one is ideal or air standard cycle analysis that we have done for the determination of air standard efficiency, and the another one is fuel air cycle analysis. Both are theoretical cycles. Now question must be arising in your mind that why at all these theoretical cycles are assuming importance. Though due to approximations, the numerical results we obtain by these theoretical cycles, whether it is air standard cycle or fuel air cycle, is quite different from the actual results that one can obtain from the study of these cycles. Okay, now the results obtained for these theoretical cycles are not merely of academic interest, but it is having certain practical importance also. Basically, the analysis of theoretical cycle is giving sort of benchmark for other cycles, for other engine cycles. The analysis of theoretical cycle indicates basically the upper limit of the performance of an engine, and moreover it shows the effect of changing operating conditions on the performance characteristics, and thus facilitating the evaluation of one engine relative to another engine. We have discussed air standard cycle and the determination of air standard efficiency and mean effective pressure, and briefly we discussed the assumptions underlying the air standard cycle. But let us revise it once more and elaborate them a bit. So air standard cycles, basically they are the cycles that use an ideal gas as the working substance or working medium. Okay, and air is assumed to be working fluid in the internal combustion engine, and as you all know that air behaves like a perfect gas, an ideal gas. So there are some simplifying assumptions that were made in the analysis of air standard cycle. The working fluid or working substance is a perfect gas, is an ideal gas, okay, throughout the range of operation, and it is bound to follow the ideal gas equation and the gas laws. That is, it is bound to follow PV is equal to MRT or PV is equal to NRUT, and P into V upon T is constant. So these equations it is bound to follow. The working fluid is a fixed mass of air either contained in a closed system or flowing at a constant rate round a closed circuit. Moreover, the value of some parameters or physical constants of the working fluid are same as they are for the air at standard atmospheric condition. Okay, so the value of Cp, the value of Cv and R and molecular mass are assuming the value that has been shown on the slide. Okay. The working medium has constant specific heats. They are not going to change with the processes. Means throughout the range of operation. Means if the range of operation of the cycle is suppose say vary from almost 1 bar to 70 or 80 bar, and in the terms of temperature suppose it is varying from 300 Kelvin to say 2000 or to 2500 Kelvin, even then the specific heats are assumed to have the same value throughout the range of operation. The working fluid is not undergoing any chemical change throughout the cycle. Means no disintegration or decomposition of the working substance has been assumed. Heat is supplied and rejected in a reversible manner, and if necessary can be supplied and rejected instantaneously. So this is assumption. Okay, the source of supply and the sink of heat rejection are external to the air, but in the actual engine energy is supplied by combustion of fuel and rejected by the exhaust of gases. Okay, so during the combustion of fuel, basically the fuel is part of the working substance. Okay, so there is no external supply of heat over here. So this is how these assumptions are varying from the real conditions. The compression and expansion processes are reversible, adiabatic. Means you can say isentropic. The kinetic and potential energies of the working fluid are neglected. And the last assumption, we can say one of the important assumption is also the operation of the engine is frictionless. That is rendering the process to be reversible. So with these assumptions, the work output, the maximum pressure, maximum temperature of the cycle, and thermal efficiency based on ideal and air standard cycle are obtained with higher value than those of actual engine. So we have discussed the assumptions that were made for the determination of performance parameters, that is air standard efficiency or mean effective pressure or anything else for the engine cycle. and basically the value that we obtained was varying a lot from that what we obtained for the actual engine. Let us say we take an example for an actual engine which was having a compression ratio of 7:1 and the thermal efficiency of the order of 30%. When for the same engine the air standard efficiency was determined, it came out to be the order of 54%. So you can basically analyze the difference between the efficiency. Actual engine we are obtaining 30%, and for the air standard cycle we are obtaining the efficiency of the order of 54%. So the large difference is there, large divergence is there, and that is basically due to the simplified assumptions. Though there were many factors that led to the difference of the value of efficiency for the air standard cycle, but even then we classify them that how or what basically were the main important factors that led to the large divergence. So basically in the case of actual engine we are not having instantaneous combustion. We are not having instantaneous valve operation, be it closing or be it opening of the valves. But in the case of air standard cycle, what we assumed? We assumed that combustion process, that is burning process, is instantaneous, taking no time, no degree of crank angle, 0 degree of crank angle. Similarly, closing and opening of the valves was assumed to be instantaneous process, means 0 degree of crank travel. Whereas in the actual case, combustion is a process that takes finite time. Means that would basically take certain degree of crank travel. Similar is the case with the closing and opening of valves. Moreover, the values of certain parameters that were assumed, be it specific heats of the working substance, they were basically oversimplified. Moreover, in the air standard cycle we assumed combustion to be complete, whereas in the actual engine the combustion never completes, and basically that is also resulting to the error in the air standard efficiency of the performance parameter of the engine. So in the air standard cycle we assume the substance to be air, and this air was the perfect gas and it was having constant specific heats. But in the actual engine the working substance is not air, it is a mixture of air, fuel and residual gases, and moreover the specific heats of the working substance are not constant but they increase as the temperature rises, and finally the products of combustion are subjected to dissociation at high temperatures. So the theoretical cycle that is based on the actual properties of the cylinder is called fuel air cycle approximation, and that is giving a better picture of the performance to compare it with the actual performance of the engine. So following things need to be taken care of in the fuel air cycle: the actual composition of the cylinder gases, that is fuel, air, water vapor plus residual gases, and this is making the working media for the engine cycle. The fuel air ratio is changed during the operation of the engine, which changes the relative amounts of CO2, water vapor, etc. Now the variation in the specific heat of the working substance or these gases with the temperature, that is making certain changes. Specific heat increases with the temperature except for monoatomic gases. Therefore the value of gamma also changes with the temperature. The fact that fuel air mixture does not completely combine chemically at high temperature, that is above 600 Kelvin, and that CO, H2H and O2 may be present at the equilibrium condition should also be considered. The variation in the number of the molecules present in the cylinder as the pressure and temperature changes. The number of molecules present after the combustion basically depend upon the fuel air ratio and upon the pressure and temperature after the combustion. Apart from these things, few other things are also important, like there is no chemical change in either fuel or air prior to combustion. Just after the combustion, the charge is always in chemical equilibrium. There is no heat exchange between the gases and the cylinder walls in any process, that is, processes are adiabatic. Also the compression and expansion processes are frictionless. In the case of reciprocating engine, the velocities are negligibly small. In all the gases except monoatomic gases, one can find increase in specific heat with temperature. The increase in specific heat does not follow any particular law. However, over the temperature range generally encountered for gases in heat engines, that is from 300 Kelvin to 1500 Kelvin or so, the specific heat curve is nearly a straight line, and that can be approximated by the equation given on the slide. That is Cp is equal to A plus Kt and Cv is equal to B plus Kt, and R, the value of gas constant, which is equal to Cp minus Cv, will be equal to A minus B. Now above 1500 Kelvin, the specific heat increases much more rapidly, and then it can be expressed by the following relation, that is A plus K1T plus K2T square, and Cv is equal to B plus K1T K2T2 square. Here the term T2 square is neglected and it becomes the same as the equation shown above, that is for the temperature range 300 Kelvin to 1500 Kelvin. Why specific heat increases with an increase in temperature? As the temperature increases, larger fraction of heat would be required to produce the motion of atoms within the molecules. As the temperature is the consequence of the motion of molecules as a whole, the energy which goes into moving the atoms does not contribute to proportional temperature rise. Hence, more heat is required to raise the temperature of unit mass through 1 degree at higher levels. This is basically the definition of a specific heat. The value of Cp and Cv for air are taken. For example, Cp is assumed to be 1.005 kilojoule per kg per Kelvin at 0 degrees Celsius and 1.264 kilojoule per kg per Kelvin at 2000 degrees Celsius. And as you know that difference between Cp and the value of gamma decreases with increase in temperature. So If the variation of specific heats is taken into account during the compression stroke, the final temperature and pressure would be lower than if the constant value of specific heats are used. Okay.
Since the difference between Cp and Cv is constant, the value of gamma, that is ratio of specific heats, decreases as the temperature increases. With variation in specific heat, the temperature at the end of compression will be 2 dash instead of 2. The magnitude of drop in temperature is proportional to drop in value of specific heats. So we can say that magnitude of T2 dash depends on gamma, that is ratio of specific heats for the given value of T1, P1 and compression ratio. In constant volume combustion, the temperature at the end of combustion will be lower, represented by 3 dash instead of 3. It is because the temperature due to given heat release decrease as Cv increases, and also because the temperature at 2 dash is lower than at 2. The reversible adiabatic expansion from 3 dash would be 3 dash 4 double dash, but the expansion taking variable specific heat into account is above 3 dash 4 double dash and is represented by 3 dash 4 dash. That is basically because the specific heats decrease as the temperature decreases during expansion. The process 3 dash 4 dash may be compared with the ideal expansion process 3-4 starting from the point 3. Thus, it is seen that the effect of variation in specific heat is to lower pressure and temperatures at point 2 and 3 and hence to deliver less work than the corresponding cycle with constant specific heats. Dissociation is the name which is given basically to the disintegration of burnt gases at high temperatures. And dissociation increases with the temperature. During dissociation, a considerable amount of heat is absorbed. This heat will be liberated when the elements recombine as the temperature falls. So we can say the general effect of dissociation is a suppression of a part of the heat during the combustion period and the liberation of it as the expansion proceeds. A condition which is really identical with the effects produced by the change in specific heat. However, the effect of dissociation is much smaller than that of change of specific heat. In IC engines, mainly dissociation of CO2 into CO and O2 occurs, whereas there is a very little dissociation of H2O. The arrow in the above equations is in both directions. It means a limiting temperature is attained when the reaction has the same rate for either direction. The reaction is then said to be in equilibrium in either direction, that is, definite proportions of CO, O2 and CO2 are present in the equilibrium mixture at each temperature. At low temperature, the proportion of CO2 is high, while at high temperature, the proportion of CO is high. For this reason, the fuel-air mixture temperature after combustion cannot go still higher because dissociation limits the release of chemical energy. This figure shows the effect of dissociation on PV diagram of Otto cycle. Because of lower maximum temperature due to dissociation, the maximum pressure is also reduced and the state after combustion will be represented by 3 dash instead of 3. If there were no reassociation due to the fall of temperature during expansion, the expansion process would have been represented by 3 dash 4 double dash. But due to reassociation, the expansion follows the path 3 dash 4 double dash, and that is because of liberation of heat. The process 3 dash 4 double dash should be compared with the ideal expansion 3-4. So we can observe that effect of dissociation is to lower the temperature and consequently the pressure at the beginning of the expansion stroke. This causes a loss of power and efficiency. Though during recombination, the heat is given back, but it is too late and some of the heat given back is lost in the exhaust. The presence of carbon monoxide and oxygen in the gases tend to prevent dissociation. This is noticeable in the rich fuel mixture, which by producing more carbon monoxide suppresses the dissociation of CO2. On the other hand, there is no dissociation in the burnt gases of a weak fuel mixture as the temperature produced is too low for this phenomena to occur. Hence, the maximum amount of dissociation occurs in the burnt gases of chemically correct mixture but decreases with the weaker and richer mixtures. Now in the figure shown, the loss in the temperature with mixture strength can be observed. With no dissociation, maximum temperature is attained with correct mixture strength, and with dissociation, maximum temperature is obtained when mixture is about 10% rich. Dissociation reduces the maximum temperature by about 300 degrees Celsius at the correct mixture strength. This figure shows basically the effect of dissociation on power. If there is no dissociation, the BP is maximum when the mixture strength is chemically correct. And the depth of shaded area between the two break power graphs shows the loss of power due to dissociation. When the mixture is lean, there is no dissociation. As the air-fuel ratio decreases, the maximum temperature rises and the dissociation commences. The maximum dissociation occurs at correct mixture strength. As the mixture becomes rich, dissociation effect commences to decline due to increased quantity of carbon monoxide. It has been observed that dissociation effects are not so pronounced in the CI engine as in the case of SI engine. It is basically because of the heterogeneous mixture and excess air present in the CI engine. Both factors will reduce overall temperature. The simple air standard theory says nothing about variation of thermal efficiency with mixture strength. But the fuel air analysis suggests that thermal efficiency will drop as the mixture supplied to the engine is enriched. Why so? This is basically explained by the increasing losses due to variable specific heats and dissociation as the engine temperatures are raised by enrichment towards the chemically correct ratio. Enrichment beyond the chemically correct ratio results in the supply of unusable excess fuel and the thermal efficiency drops rapidly. It would therefore appear that thermal efficiency would increase as the mixture is made weak. However, beyond a certain weakening or certain leaning of the mixture, the combustion becomes erratic with the loss of efficiency. Thus, the maximum efficiency is within the weak zone near chemically correct ratio, and this gives rise to the combustion loop as shown in figure, which can be plotted at different mixture strengths on an engine running at constant speed and constant throttle setting. The effect of common engine operating variables on the pressure and temperature within the engine cylinder are better understood by the fuel air cycle analysis. Now the compression ratio. The fuel air cycle efficiency increases with the compression ratio in the same manner as the air standard cycle efficiency. And the reason behind this would be the more scope of expansion work. The variation of indicator thermal efficiency with respect to equivalence ratio for the various compression ratio has been shown on the figure. The equivalence ratio is defined as the ratio of actual fuel-air ratio to chemically correct fuel-air ratio on mass basis. The maximum pressure and maximum temperature increase with compression ratio since the temperature T2 and pressure P2 at the end of compression are higher. As the mixture is made lean, the temperature rise due to combustion will be lowered as a result of reduced energy input per unit mass of mixture, and this will result in lower specific heat. Further, it will also decrease the losses due to dissociation and variation in specific heat. The efficiency is therefore higher and in fact approaches the air cycle efficiency as the fuel-air ratio is reduced, as shown in this figure. Fuel-air ratio affects the maximum power output of the engine. As shown in the figure, as the mixture becomes richer after a certain point, both efficiency and power output falls or drop can be seen from the experimental curve. It is basically because in addition to higher specific heats and chemical equilibrium losses, there is insufficient air which will lead to the formation of CO and H2 during combustion, which represents a direct wastage of fuel. However, the fuel-air cycle analysis cannot exactly imitate the experimental curve due to various simplification of the assumptions that are made. At a given compression ratio, the temperature after combustion reaches a maximum when the mixture is slightly rich, as shown in the figure. At chemically correct ratio, there is still some oxygen present at the point 3. Because of the chemical equilibrium effects, a rich mixture will cause more fuel to combine with oxygen at that point, thereby raising the temperature T3. However, at richer mixtures, increased formation of CO counters this effect. The pressure of gas in the given space depends upon its temperature and the number of molecules. The curve of P3 therefore follows T3, but because of the increasing number of molecules, P3 does not start to decrease until the mixture is somewhat richer than that for maximum T3, that is about 20% rich, as shown in the figure. The exhaust gas temperature P4 is maximum at the chemically correct mixture, as shown in the figure on the slide. At this point, the fuel and oxygen are completely used up, as the effect of chemical equilibrium is not significant. At lean mixtures, because of less fuel, T3 is less and hence T4 is less. At rich mixtures, less sensible energy is developed and hence T4 is less. That is, T4 varies with fuel-air ratio in the same manner as T3, except that maximum T4 is at chemically correct fuel-air ratio in place of slightly rich fuel-air ratio, as in case of T3. However, the behavior of T4 with compression ratio is different from that of T3. Unlike T3, the exhaust gas temperature T4 is lower at high compression ratio because the increased expansion causes the gas to do more work on the piston, leaving less heat to be rejected at the end of the stroke. The same effect is present in the case of air cycle analysis also. The mean effective pressure increases with the compression ratio. It follows the trend of P3 and P4 and hence it is maximum at a fuel-air ratio that is slightly richer than the chemically correct ratio, as shown on this figure. With this, we finish the analysis of fuel-air cycle. Thank you.